Say again? I'm staying until the end of the day. Yeah. Is it about the end of the month or?
It's about somebody's rival.
Yeah, so that's one. Someone else, no, the one I'm thinking about.
I think that should be perfect.
Recommended
Well, turned out that wasn't true.
Yeah.
Perfect. You should be good to start.
Should we go? Can I start? Okay. Thanks everyone. Thanks for having me. I want to first apologize. This is not 101. This is a seminar, but it's about a tutorial. So maybe that could convey some one-on-one-ness in the content. So if you want to learn more about this and do it a bit more slowly, there's a whole paper. Slides are available as well. This is a quine of sorts. You can see them on Zuleb. Otherwise, I'll start. It's one paper, but there's more further work in this. Why there's a few more people listed here, and hopefully I'll get there. I don't have to get to the end of the talk. I'm here for the rest of the day. You can talk to me. It's more important that you understand, so ask questions. That goes for the people online. Can they hear me? I'll let you check, but I assume that they are. Great. Okay, so this talk is about representing syntax. It's about mostly representing syntax mathematically, but there is a little bit about representing it computationally. So what do I mean by this? Let's look at a little piece of mathematical syntax. This could have been a program, just maybe more two-dimensional thing here. I should talk about two-dimensional syntax a little bit too. So this formula, I'm not going to go into the semantics because this talk is just about the syntax. So concrete syntax means, representing just the symbols as they are, usually flattened out into a line. So we kind of collapse this two-dimensional syntax into a linear representation. Okay, that's fine. And if you go into old logic books, for example, you'd see people prove theorems about concrete syntax, like the number of matching brackets and so on. I think that's one of the least interesting things you can say about syntax, but even on concrete syntax, actually, someone was arguing we should be talking more about concrete syntax over the last few days. But I'm not going to talk about concrete syntax. I'm going to look at more structured representation. So the next level up, we teach it in our introductory course, is abstract syntax, just as syntax trees. Okay, and here we have the topmost operation plus, and then sigma on the left, integrals on the right, and so on. And what this doesn't take into account at the point of this talk is the binding structure of your term. So for example, the variable I here, it appears bound, and here it appears in a binding occurrence, and we can't tell them apart in this representation. We have to do something else on top to track that, and slightly more structured representation for syntax with binding is one where we think of those names as pointers. So here is still an open term, the same term. I have some names in context, and then I have the binding occurrence here on the leg here, and this pointer points at that binding occurrence, and then at here, and then at if I have a variable, I can point at the context, and so on. So it's just a much more structured representation. Question?
That's a good question. Why have you not separated the NX?
Oh yeah, I should have. Yes. I noticed it on the way here, but yeah, yep, I agree. This leg should be like the D leg, or could be an operator with it. Yes. Yep.
In the abstract syntax of binding, N is unbound. So where is that from?
Yeah, so I really should put it up front, but then all the arrows go across the term, so I put it afterwards. And in a sense, this is one of the things that kind of shouldn't matter. You should have multiple representations. You should be able to kind of move things around, so long as you have the basic primitives of abstract syntax, right? And this is with binding. And this is really what this talk is about. Okay, great. I'm loving all the questions. Right, so I'm going to use as a running example the core by value lambda calculus, mostly because people know it. So what do I mean by the core by value lambda calculus? I actually mean a bunch of calculi. You have base types, function types, records, variance. You can add some more types. I'm not going to consider more types in this talk. And what's interesting about the core by value lambda calculus is that we have two kinds of terms. We have values and computations. Okay, very often you just define terms and you single out the values as a separate syntactic class, but however you do it, when you develop the meta theory of the core by value lambda calculus, you have this distinction between these two classes. Okay, and okay. Now, when we think about the language, I mean, you even say it, right? You can add this, you can add this, you can add this, you can think about all the different fragments of the language, right? And if you do say semantics, you do actually think about your semantics like that, right? You kind of say, I have my base fragment, and there's some kind of model structure that it corresponds to. For example, a strong monad of mechanism category. I'm not going to go into it, you don't even need to know that for the rest of the talk. But then different fragments of the language, sequential, functions, variants, and so on, have different kind of requirements on the model, and you kind of take them kind of a la carte. And you can kind of get the semantics, the semantic theory to work out. Okay, so kind of you get into this dream of, you look at all the fragments of the language, you can kind of mix and match the semantic structure, you can mix and match the syntactic construct, and then, we have this unified understanding of how the world works, right? So that's kind of a dream. It's not my dream, it's been there for decades. I think I'm tracing it to the Gogan-Thatcher program, but it probably is earlier than that, especially in categorical logic. That's probably even earlier. Okay. The reality is a little bit more nuanced, okay? So when you develop the meta theory for this kind of setting, there's a bunch of results you would usually prove in a programming language setting. So you would prove some substitution lemma, a compositionality theorem, and then you'd show that your relational semantics is sound with respect to your operational semantics. Similarly for adequacy. Okay, and out of this you get the profit. Okay, but if you actually look at the proofs, these two results are actually interesting, and they change the more you add into the language. These two feel like you're just doing the same thing again and again and again and again, and it's just kind of tedious and boring. Okay, and so you might want to not make it tedious and boring. Okay, and I'm going to come back to that later in the talk. So what I mean by substitution lemma and compositionality, so I mean this specific result. So I'm talking about the semantic substitution lemma, which is syntactic substitution corresponds to semantic composition. Okay, if I have a term m and I substitute into its variables, that should be the same thing as taking the semantics of m before the substitution and composing that after the semantics of the substitution. Okay. Compositionality usually says the semantics is independent of the syntactic constructs on the semantics. So if I have a composite term, C with m plugged in the hole, that's the same thing as taking the semantics of the term with the hole and the semantics of m and plugging them together. Okay, and put a sketch of the proof. So usually to prove this, first of all, you have to prove a kind of a syntactic substitution lemma before you even start, and that involves several inductions over your syntax. Then you do induction over the semantics, and that also typically involves several inductions of all your constructs. This one is a little bit different. Kind of the tedious thing is adding holes, defining how to do substitution in the holes, capturing some variables, not capturing other variables, defining how all that works out. And then after you do that, then it's a straightforward induction, but you have to kind of do all this preparation work kind of from scratch again. Okay, so the dream, again, another dream. Would be nice if all the tedious bits were free. Okay, I'm not going to say free. I'm going to say syntactically scalable. Okay, so what I mean by that? I mean that as I add more constructs to my language, I need to do extra work per construct, but maybe not everything from scratch again. Okay, so kind of do the thing you need to do when you need to do it, and then set up all the other theories so that everything talks to each other. Okay, so I think that's a bit more realistic. And in a sense, this is another instance of the expression problem. So the expression problem, the name was coined by Wadler, but it's actually, I think the first instance is Reynolds in a paper from 75, and he even says it. It's not like he hides it. He posted it to one of the Java generics mailing lists. So what is it? You have a language and you want to extend it with additional constructs, so add some syntax to the language. and then add functions or properties of that extra syntax. Okay, like think about an interpreter, you want to interpret the extra syntax. But you don't want to recompile your previous modules, or in the setting of today, you want to keep both languages around. Okay, I can't just go and modify the code. I need to somehow keep all my different modules together and kind of combine them together. And even as you wrote it, there were existing solutions. I think this was early instance of Scala mixing, if I'm not wrong. Krishnamurti, Felizen and Friedman had a visitor pattern in Pizza, and then I think Zodiac was the language that they implemented the other way around. And what in that post suggested a kind of a solution based on recursive generics, and a few, 10 years later, Walter Sriestra suggested data types a la carte using copyrights of signature functors. And I'm happy to learn more history to inform this slide or future versions of the paper. Okay, I'm not claiming this talk is about solving the expression problem, because this is really solving it in the context of an existing programming language. This is more in maths, but it is the same issue. Okay, it's how do we kind of keep all the different maths together and putting every piece of work where they are. Okay, now that problem or that situation already has a solution. It's called second order abstract syntax. I mean, there's other solutions out there, but I'm working off of this strand from '99, and this is a kind of initial algebra characterization for abstract syntax with binding over substitution. And it's robust to both extensions, for example, polymorphism or substructural types, but also mechanizations. I think this is the run room where I can point at the authors and say they did it. And later, Marcelo and Dima built off of that. I mean, Marcelo told me he read your paper and he kind of reverse engineered some bits in it. So thanks for that. Okay, and it works really smoothly for call by name. It just doesn't cover call by value. Okay, and I'm going to touch on it in a few slides, but really kind of the reason, the intuition is, in call by value calculi, we substitute both in values and terms. Okay, we have these values and we have those terms, and we substitute in both of them. But what we substitute for values, for variables, is only values. Okay, those values inside can contain computations, but kind of the top level thing that we substitute is only a value. And I think call by value is actually not the best example for this. Call by push-all is much better example. And in fact, I mean, if you look at richer languages that I've not tried doing in this setup, there are syntactic things that you don't bind. For example, if you look at contexts, independently typed languages, right? You're not kind of binding over contexts. Usually, you could, but you don't have to, right? And so to me, this is a very natural distinction to carry around, and the original theory just doesn't account for it. So, I mean, I reached out to Marcelo when we thought about this, and he said, oh yeah, it doesn't cover call by value, it would be nice to do it. So we did it. So this talk really is not too much about the delta. I think the delta is not quite big, but it's more about the tutorial of abstract syntax. And I think very unusually, the paper that I linked to has almost all the proofs. So if you have a grad student, or if you are a grad student, start at the beginning, get to the end, jump to the appendices, but everything should be there unless I made a mistake, or if something is omitted, it's because it's similar to something that I already did before in that paper. Okay, so it's kind of geared to one-on-one-ness, I think. It's just that if I had to really do it one-on-one fashion, it will take me like 3 hours rather than one, and I want to finish on time. So that's that. Okay, so kind of the slogan for call by value, of really for this talk, is that from the perspective of substitution, this is just about syntax and substitution, values are first class and terms are second class. Okay, and this kind of distinction between first classness and second classness is the thing I'm going to carry around for the rest of the talk. So let's look at the formal definition. Okay, and carry it around. So what do I mean by that? So a sorting system is the thing that tells me what sorts of things I have. I mean, think types, but it doesn't have to be types. Types of terms, really. Sorts of terms. Okay, so I have two kinds of sorts. I have the first class sorts and the second class sorts, and they live together as a coproduct. Okay, or disjoint union. Okay, so two examples, the two running examples, or really one running example. If I look at all the call by value types, they embed into all the sorts of the running example, which are one copy of the call by value types with no annotations, which stand for values, and then another copy of the call by value types with a computation tag on them. Right, so I have two copies of each type. It's A in comp A, and I'll be keeping track of them as I build the syntax. Okay, so I have my first class types, the value, and second class ones are the computations. In Kobayashi push value, it's much more natural, so I think it's much a better example, but people don't know it as much. Okay, there you just take all the Kobayashi push value types, and they automatically get separated into values and computations. Those are the first class and those are the second class. Okay, but I think fewer people know Kobayashi push value, maybe not in this room. So I'm not going to use that as one example. Any question about this? So a sorting system is really two sets living together in a union, and we have two embeddings from first class sorts and from the second class sorts into that set of overall sorts. Any questions about this? Okay.
Is it always a disjoint union? Because here
I'm asking it to be a corporate diagram. Yeah, I'm going to keep it a disjoint union. There's a no, I don't know. There's more. There's the tangents to go on, but I won't go there. Yes, Nancy?
Can you do subsorting?
No, that's the tangent that I didn't want to go on. So yes. Okay. Okay, you ask. So the subsorting is you have two sorts, and you ask for the embedding to be homomorphism with respect to the operations you have on the subsort, for example, and then you would get the subness to work out. I think, but I've not changed all the calculations. Any more questions? Okay, so really kind of summarizing in one slide the core contributions and keeping it high level. Okay, but we'll go too slowly to this. Okay, so we have our sorting system, and what I want to show here is how the classical theories, economic abstract syntax, get generalized once you add this second class sorts in a theory that I just wanted to put them side by side, so we call them modular abstract syntax trees rather than SOAS, so you can kind of compare them SOAS versus MAST. Okay, but it's really a generalization of this one just to be with the second class sorts. So in the SOAS case, the homogeneous case, I have no second class sorts. Okay, and so the two sets are the same. I could give them different names, but that doesn't matter. And in the heterogeneous case, which is what we talked about earlier in the previous slide, I have two sets and they live together. Okay, so what happens in this theory? The way in which we organize both our syntax and our semantics is through presheaves. So presheaves are just functors into set. So they index in the setting by two kinds of things. So first the sort, and then the context of variables you have at any given moment. Okay, and they have a notion of renaming, and we're going to get to that later when we go in between the weeds, which is why I stuck the op here, but that is for later. And for each collection of sort S and context gamma, I have a set. So for example, the syntax, right? So the collection of terms of sort S and context gamma is this presheaf. Okay, and in the semantics, the collection of semantics of sort S in context gamma in some category C is going to be all the morphisms from the semantics of gamma to the semantics of S. So what's happening here is both the syntax and the semantics live in the same universe, and so we can talk about syntactic substitution and semantic substitution and how they relate to each other. And that's the whole setup here. Okay. What happens when you add multiple sorts? Then things start to change. Okay. So what you have now is presheaves that are indexed by all possible sorts, but the context can only contain the first class sorts. Okay. And you can break it down in different ways, and in fact, the different ways you break it down, sometimes one is more comfortable, sometimes the other, so I'm actually going to switch between them. So maybe pay a little bit more attention just now. So I can, because I have both the first class sorts and the second class sorts here, I can actually replace it by saying I have two presheaves, one on a homogeneous one for first class sorts, okay, and one that is for every second class sort indexed by a context of first class sorts. Okay, so I can just separate the two sets of sorts. I'm going to use the restriction notation to say, talking about only about the first class fragment or the second class fragment or the total fragment. Okay, any questions about this? Okay, so if the second class sorts are empty, then this just goes away and you end up with the original piece of theory. That's how you generalize. Okay, so just kind of squashed everything up. There's two more ingredients I want to talk about. So there is the variables, and concretely we know what to write. The variables of sort S in context gamma are all the variables of sort S in context gamma. Okay, but when in the two theories, they kind of live in different universes. So the variables are just appreciative in the classical theory, and so us. But in MAST, they only live in the homogeneous appreciative fragment, but not in the second class one. So somehow you will have to kind of separate things into first class and second class and kind of work out how they all interact. And that's really what the contribution is kind of refining the theory to let all of this happen. Okay, the ingredient that's equal for both one is a signature functor. Okay, the signature functor, if you're doing coalgebra, it's that kind of gadget, right? You're saying, given a collection of subterms x, O of x tells you what possible thing you can construct with subterms in x. What's special about this theory, and sometimes it kind of gets squashed to the side, and I think this is kind of this is the most central bit in it that gives you the modularity, okay, is the pointed strength. If you go read the papers, it's actually quite hard to find it, but this is what makes everything tick. So when we get into the weeds, I would like to spend, if I spend any time, I will spend it on that, because this is really what gives you the modularity. Okay, so what is the strength? Let's start with just the overall type. So I have a P and I have a var, and the var goes from variables to A, and the strength says I have O of P times A to O of P times A. Okay, I just said words. Let's talk about the meaning. Okay, so what's happening here is this tensor, and this is the thing that drives the whole theory, takes a term or a value of this type, and then a closure or environment of this type, and pairs them together. That's the input to a substitution. Okay, so what this thing is saying is I have a term, one of the O's and subterms in B. Okay, and I want to substitute into it something from A. Okay, so for every variable that appears in the term, I have a value of type A, and I want to kind of put them together. And moreover, this A can contain variables. There's a map that tells you how each variable can map into A. Okay, so A is something that can contain variables in it somewhere. Okay, so this is a closure that can contain variables. And what the strength tells us is how to move that environment under the term. So I get a term that now contains subterms that are both a P and an A closure. Okay, and if we somehow went under a binder, we need to somehow weaken that closure to make sure that we haven't captured the variables we just bound. Okay, so each construct tells us how to substitute under it. And it's kind of flexible with respect to all possible A's, all possible P's. And that's what gives the modularity. Question?
Yes, again, very stupid question.
Yes?
Why would you call that a tensor? So tensor, they usually associate with separating two similar structures, but now you're describing one type of structure being fed into another structure. So why is it not a composition of some other sorts?
I mean,
it seems to be asymmetric. You get even.
It's asymmetric only the first level. Once you continue tensoring, it becomes more uniform. You get closure, 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 closure. Should do it stage left, sorry. You get the term, and then the more you tensor, you get more and more and more closures. So you're correct that at the bottom level, it's different, but all the rest, it's actually quite uniform. And in fact, in one way to understand it is through actions, and we'll get there when you go in the weeds, and then you'll see that there's a tensor that's very uniform, as you say, pairing things together, and then there's an action on terms, and then that's of a different nature, and that's part of the thing that makes the theory tick, actually. So that's a really nice observation.
Is it an asymmetric operator?
It's very non-symmetric, yeah. But both of them, even the one I'm going to talk about later, is non-symmetric. Any more questions? Yes?
Yeah, I was going to ask about binders because here it looks like the A is preserved exactly like it was when you push it through.
But under the O can shift the context. You see, so O can bind more variables, and then when you put it through, it has another variable that you have to do something about. And so what you have to do is weaken the A by adding another variable that gets mapped to itself.
Yeah, the tensor actually dependent on the size of the context.
Yeah, these things are all scoping now.
Yeah, everything is copying us. We'll get there when we go into the weeds. I'm just trying to kind of put the theories two side by side. I will have a slide with more details later, but I'm just trying to map the contribution. That's okay. There's one more line to this slide. Okay, but before that, so the strength in the classical theory, we have both P and A being R structures, but A has a map from variables. Here, because of this distinction between first class and second class, P and A are actually of completely different sorts of things. P is an R structure, but A is a homogeneous structure that can contain the variables, and as you say, right, it's very non-symmetric. So you kind of have to have an action of sorts. Okay, and then to account for substitution, in the classical case, you have a monoid. Okay, so both the model and the semantics can interpret variables, but also there's a substitution operator that takes the inputs and kind of does the substitution and gives you something in M, and you have all the properties for a monoid. Here, it gets more refined. You actually have two kinds of things. So on the first class sorts, you have a monoid, but on the second class sorts, you have an action. This is a right action. Okay, and they both kind of live together. Okay, and they're mutually recursive, so you can't really separate them. Okay, this follows some earlier work by Marcello and Daniele Churi, where they could separate them, and then they talked about actions. First, you define the monoid of syntax, and then you act on another action. But here, everything is mutually recursive. Okay, so this is just kind of side by side, before this paper, after this paper, and this is how you generalize it. So if there's no second class sorts, this component just goes away. All we're left with is the monoid of the original theory. Okay, any questions about this? Great. Okay, so contribution in a very high level, this is a seminar again, not a 101, takes SOAS, add second class sort, get MAST. Okay, and actually we could, you could have done this work 20 years ago, okay, but you couldn't have done it like this 20 years ago. So actually we took a lot of shortcuts because since then some things have come to be. So in particular, Nicola Gambino, so the theorem of Martin and Glowinsko, worked out the structure of substitution not when you have just one set of sorts, but when you have multiple sets of sorts. And again, here we have two. So already you start thinking about multiple sets of sorts, and then it's not too difficult to say, oh, what happens if you have more? And then it's that theory. Okay, so all the properties about the tensor product being associative and right unital, left unital, closed, all that kind of comes really cleanly from this theory. And it all comes from the theory of Prof functors. So it's really all very clean. I did not have to do any complicated calculation on this bit, which I like a lot. Because usually you have to really mess around with variables to get it all to work. And here I really did not have to do any of that, which was nice. We changed the kind of the tensor product from a monoidal category to an act category. So there's two kinds of tensors in place, and they act on each other. And the syntax itself, as I said, we generalize from monoids to actions, or something that's called modules. I think I'm going to stick with actions for the rest of the talk, but some people are happy with modules. Okay, the paper itself is is really, as I said, the tutorial style. So if you really want to just walk your way through all of it, almost all the details should be there. I mean, I didn't write all of it, all the details, but hopefully you could fill in most of the details. And there's a case study. I mean, for those who like numbers, I took this call-by-value language, we took it, and then we looked at all the possible fragments. Basically, you add fragments until you have more than 100 cases, and that's what happened there. As I said, there's two papers, so I'm also, me and Granops and Iftod, we're implementing just the computational fragment of this, so just the representations and all the substitution operators in Idris. And we have a nice little case study. I might be able to come back to it later in the talk for designing FFI binding for a scintilla. So I don't know if Wen is online, but we were borrowing heavily from Schmitty when we were thinking about this. So thank you, Wen. Any questions about this? So the next slide is talking a little bit more, still at high level, about substitution, and then if I have any time left, I'll go into the technical details, but we don't have to. Yeah. Okay. So what's the kind of the capstone of the theory, the takeaway message, the end goal? Okay, so the end goal is this representation theorem. Okay, that says that the abstract syntax with substitution have a universal property. Okay, so the abstract syntax itself has a universal property. It's given by some the thing you know you want to do, the kind of the Brown representation of your end functor with variables and so on. But what's interesting is that substitution also comes into it, and it's that universal property of substitution that gives you all the other bits for free, or almost free. Okay, so the theorem says abstract syntax with operators from subsignature functor O, a strong signature functor O, and holes in some pre-sheeted holes H, amounts to what? The free substitution O action over H. So we're going to define that a bit later, more formally, but really what you have is you have the syntax, SH, okay, and then there's 4 different things you have in it. So you have the way that the variables embed into the first order fragment. Okay, you have the substitution operator. So I have a value, a term from the syntax together with the closure of values of first class terms, and I want to substitute them to get the term. I have the inclusion of holes in it. Okay, this is how the holes embed. And for every construct in a language, I have an algebra structure for that construct. Okay, so those 4 things, and they interact with each other, and that's given by the substitution O action bunch of axioms that will come later. Okay, and the point is that if you can then show the universal property of the syntax with all those 4 operations being the initial one. Okay, so in the process you prove the syntactic substitution lemma and so on. So you really do all the things you would do concretely when you represent these things. But I guess you can do it abstractly solely through the interface of the strength here and all the kind of the theoretical structure. And because this is a free construction, okay, that gives me a monad. Okay, and the class extension operator for that monad, for the O action monad, for your action monad, that's meta-variable substitution. Okay, and if I internalize it, so I need to show it a strong monad, I need to assume one more thing about O, then actually I get it's a strong monad, and you can really kind of do meta-variable substitution through a monadic kind of notation, which I think is pretty cool. So that's the capstone. So what? Okay, so this is the point. Okay, and I'm calling it a propaganda because I'm not going to actually give you any reason to think like that. Okay, so the propaganda is this. Compositional binding respecting the notational semantics amounts to giving a substitution O action. Okay, that means giving a model M together with a way to embed variables and substitution and a semantics for each construct. Okay, and the reason this is a propaganda is because all I'm going to do is show you a bunch of examples and say, think like this. But I'm not going to convince you why this is a good reason to think like this beyond this is how everything we do so far fits. Okay, so the notational semantics for terms with holes in H is the unique substitution O action homomorphism over H. Okay, so I have my syntax that has the structure, and I equip the model with this structure. Therefore, there exists a unique map, and that's the notational semantics. Okay. Any questions about this? So what I'm going to do now is I'm going to go back to the goal, the tedious bits, and improve them just with this information. Okay, so I said it would be nice if the 3 bits were, easy. Okay, and so let's make them easy. In fact, we're going to give them one-line proof. Okay, so let's look first at the substitution lemma. So we have M with substitution theta. We want to show that this is M, semantics of M composed with the semantics of theta. Well, this is equal to the substitution operation on the input to substitution M with theta. Okay, so concretely, each of the examples that we do, you see that this operation is exactly this, kind of the capture avoiding substitution that you would employ. The semantics is the substitution action homomorphism, so they preserve substitution. Okay, and the substitution on the semantic side is just composition. Okay, so now this is now even interesting, not even boring, I think, and it's just a one line. Okay, any questions about this? This is kind of the point. Okay, compositionality, similar style. So take C, plug M. So this is meta-variable substitution. Huh? So let's look at C with the meta-variable for M in it. Meta-variable substitute M for M. and the semantics, sorry, Kleisler extension is homomorphic, therefore this gets preserved, and if we define the plugging operation on the semantics just as the Kleisler extension of the free O action, we get this equation. Okay, so the semantics of a composite term depends only on the semantics of its parts. This is the thing we want to prove. Okay, so this is a bit more sleight of handy, but not too much. Okay, so I started by saying, you know, what is this talk all about? I said, so what we really want to do is make it the boring bits not boring and simple. I've shown you how that would happen if only I could deliver the theory that does that. I mean, all the details are in the paper, but I can actually look a little bit into the piece of structure that goes into it. So if you're going to use this theory, what do you need to understand in order to use it? Yes, there's a question
We have
online.
a question from online. So this is the strength, right? I think about this.
This one?
Yes, I believe so.
They want to unmute and ask. Or...
They asked, so this is the strength, right?
What does this refer to?
So either I think maybe looking at the Kleisler one. So the Kleisler one. So if you can sort of pull the Kleisler operation out of the semantic brackets, is that the strength that we have seen earlier in earlier slides?
No, that would be a different. That would be the strength of the free O action monad, but I'm not using that here either. Yeah, we'll have a concrete example for the strength for the signature functor in 4 slides, I think. 5 slides.
Thanks.
I mean, so it feels like the bulk of the work is hidden in that substitution action homomorphism assumption, right?
Here.
Yeah, which I get for syntax, you get for free.
I mean, when you prove this, you have to. So
Yeah,
you work quite hard to
yeah.
prove it. What you do is you define both this. You kind of prove this the substitution lemma for the syntax, and you define the semantic respect to any other model, right? And along the way, you kind of show that any kind of semantics you can fold into the traversal, and it's the fact that you're ranging over all possible semantics as you do that. That's what gives you the extra oomph, then rather than just reasoning completely syntactically. Yes. So when you phrase the strength, you don't only explain how substitution will work on the syntax. You explain how it works on all possible semantics is for it. And we'll see that happen in a few slides. Yes. Any more questions? Okay. So this is a busy slide. Okay. But what I want to, the thing I want to take away from this is the strength at the bottom. Okay. And you'll see it involves all the ingredients before it. So, okay, so kind of the heart is the strength. Okay, but we really need to go slowly through all of the other stuff in order to explain how it all moves. Okay, so I'm going to kind of make it go away, and let's go just very slowly, line by line, through this slide. Okay, so remember we have this sorting system. So we have the first class sort, the second class sort, and they live together in a big set of sorts as a coproduct. Okay, out of the first class sorts, we can generate a category of context. So if you implement this is exactly the thing you would do. You look at lists of sorts, and here I'm putting variable names. They're completely fictitious. I just want to be able to say the first, the second, the third. In implementation, this is literally what you do. Okay, so the variable name, it looks like I'm carrying a nominal representation here. No, this is just a bound, but I don't want to say first, second, third. I want to say X, Y, Z when I talk to you. Yeah. Okay.
So like the sorts are sets, right?
So the sorts are elements of the set of first class sorts.
Yes.
Yeah.
That's like property inside.
It's a couple like inset, yeah. This is inset, yeah. Okay, and the renamings, so the context and the renamings form a category, so you tell you what the morphisms are. So the morphism from gamma to delta in this category first step is, I use this mnemonic, right? So for every variable in delta of sort S, I need to pick a variable in gamma of sort S. Okay, you can choose this direction, you can choose the other one, we can argue over which is which. It doesn't matter, you choose one and then you stick with it, and that's the point. Okay, so I chose this because I sit here. No, I mean, a better reason is these together have a universal property, which is the free product completion of the set of sorts. But even though I'm using it to cut corners a lot in the paper, I'm not going to touch on that in the talk. Okay. Great. So now the R structures are, so where the syntax is going to be an R structure, and if the semantics is going to be an R structure, and these are going to be this kind of heterogeneous presheaves. Okay, so they're indexed by any sort and a context of first-class sorts. I'll give you back a set, and we looked at some examples already. And we think of kind of an element little p of ps gamma as some semantic value or syntactic value of sort S that knows about variables in gamma. Okay. Actually, this is a mistake here. This should be first struct. It's a type of variables are first struct. Sorry about that. To fix that. Okay, so far we've kind of seen in the earlier slides. I'm just making it a little bit more concrete, telling you what this perp construction is doing. Okay, now comes the tensors, and as you said, there's two of them. So the first one, the basic one, takes an R structure, so a heterogeneous structure and a homogeneous structure, and bangs them together to get a heterogeneous structure again. Okay, so what do I need to tell you? I need to tell you P tensor Q, what is it at sort little s in context gamma? Okay, and what is it going to be? It's going to be a little p from P and a tuple of Q's theta. Okay, because we really think about those theta as a closure, Q value closure. Okay, so P is an element, so it's really a triple P theta with some kind of intermediate delta. Okay, so the variables that P knows about are from delta. Okay, and theta tells you what to give to each delta variable. Okay, for each delta variable, I'm giving a Q value of the correct sort in the external context. Okay, and you could just take it without the quotient, so I'm quotienting this. Okay, by these basically these equations or through the quotient. You can take it without the quotient, but then you won't have a monoidal structure. You have a skew monoidal structure, which means other things will happen. But if you think of this as the input to substitution, quotienting the input means imposing equations on the output of substitution. So we're building in some laws of substitution from the get-go. It's kind of the input type to substitution if you wanted to validate some equations, and the equations are basically these ones. So what are they? If I have a weakened P, so theta now contains more values than I need in order to substitute into P. P doesn't know about as many variables as theta has. Well, you can just project out the bit that P knows about. Okay, those two inputs should give you the same output from substitution. This one, which is just a representative one, if I have P, but P has two different variables, x prime and x double prime, but actually they're the same variable in this instance. Okay, then I can take theta and kind of duplicate it, take the value that goes for x and put them in both for x prime and x double prime. In substitution, you should also respect that. Okay. So far so good. So this gives me a tensor product, or this functor, this kind of mixed tensor product. And kind of the thing that does all the heavy lifting is the other tensor product, which is the pointed one. So what happens here is I'm basically saying, given a P and an A, that is a first class structure that knows about some variables. Okay, so this is the input. Then forget about the variables, just look at P together with A. Okay, and that's what the tensor is doing. It looks bizarre, but you'll see in a second why, and it's this thing. This now means that the strength is parameterized not just by the P and the A, but also by the way in which variables are made in A. It gives me more freedom to define the strength, to define substitution or a construct. Okay, so it looks weird, but actually it's the thing you need. Okay, you need to talk about, I have a structure, a piece of maybe syntax, maybe semantics, and I'm trying to put it together with something that knows about variables. Okay, and of course, how are we going to put it together? I'm going to put it together by just taking the closure of that thing, that A. Okay, but I need to remember how the variables get embedded into it. I have an example in the next slide. Yeah, I have plenty of time. Okay. And then substitution, we talked about those, so we get maybe later, maybe afterwards. So because this is really the heart of the theory, let's look at a concrete example for the strength. I think this is the thing you really wanted. So let's look at an example for an O functor, an endo functor over R structures, together with a strength for it. So for example, I'm looking at the let construct. Okay, let x column A equals something in other something, and that really exercises almost all the ingredients you want to have. So I like this example a lot. Okay, much better than lambda abstraction. Okay, so so if you want to add the let construct to a language, well, the let construct in call by value is a computation. Okay, so I'm not adding anything on the value sorts. Okay, so the signature says, given any collection of subterms x, I'm not adding any more constructs at the value sorts. Okay, but at the computation sorts, okay, for every intermediate type A, I will add another construct that says you can abstract over an intermediate result of type X, and then it's going to be basically a pair of the intermediate computations, or a computation of type A in context gamma. Okay, and the body of the let, computation of type B, but in an extended context gamma with X. Okay, so that's the end of functor signature. What's the strength? Okay, so the strength, again, I'm applying this. I have a sec p together with a tuple for it, theta. Okay, and yeah, this is the t, this is the theta. And what I need to do is to say, well, what does this t look like? Well, it looks like a let with a p in it and a q in it. Okay, where the p knows about the variables in delta and the q knows about one more variable x. Okay, and I have my theta. And what I need to do is to follow it into the let, right? So I need to stick the theta into the intermediate computation and into the body. Okay, so here the context hasn't changed. I can just leave theta as is. But here I need one more variable. Okay, and that variable is going to be exactly that extra variable I got by extending the context. Okay, so if you kind of forget about the fact that P and Q are semantic abstract presheaves, this is the rule you would write when you're writing out in full how to substitute to let fully formally. But because we're ranging over all possible presheaves presheaves P and all possible pointed presheaves var, okay, that's exactly the modularity that lets me not worry about anything else. Okay, so I get that each syntactic construct defines its own binding, renaming, and substitution structure. Okay, and it's very easy to miss this because there's lots of other maths. Any questions about this? There's lots of examples in the paper, but I think this one is really the, yeah.
So first you needed to prove that this extension made secx preshift.
Which we the renaming, yep.
Yeah, so you're doing more or less the same work as the strand?
I mean,
the way you're pushing the renamings in is very similar.
In the next slide, I won't even do any of that work because you can use combinators to get all of that, right?
Right.
But yep. But in the proof, when you need a renaming, you have a renaming. When you need a substitution, you have a strength.
Yeah.
That's where these things come up.
Mhm.
Okay. And one of the nice things in Dima's thesis is that he looks at this is Dima Shamoshvanchev. He looks at endofunctors over families, okay, and he shows that you can lift them under some conditions, so you can kind of get a auto renaming thing for free if you have the strength. Okay, but check the thesis. I don't want to misquote his work. Okay, so there's also combinators, so you don't actually have to do it if what you need is just some kind of a very vanilla binding signature or universal syntax of sorts. I mean, these are you don't even have to write that. Okay, but if you did need to write everything, that's the interface you need. We're now 7 minutes to go, so I think what I'm going to do is I'm going to not go through the rest in detail. All the details are in the paper. As I said, it also has a case study. You can look at the paper. I want to spend maybe 2 more minutes about the work in progress we're doing, and then I'll take general questions, and then we'll stop. Is that the right timing for the day? Yeah. Okay. So what are we doing with this? So this is stuff I've done already. What's coming next? Okay. So really based on Dima Shamoshvanchev's thesis, we implemented the same kind of computations in Idris. So you implement those species, you implement those endofunctors, and you can get these abstract syntax trees with meta-variable substitution, and it's all very generic. It's kind of nasty to work directly with it, but that's not the point. I just want to get the modularity first. Okay, so we implemented Idris, and kind of a killer app, as Dan Geeker likes to say, is an SMTlib foreign function interface. So what's interesting about SMTlib is that the query language has S expressions, but it's really 29 theories. Actually, there's a little bit more, but they've added some more high order functions to it. And some of them has bindings, some of them don't. And if I kind of look at all the possible combinations, there's like quite a few, and I want to have all of them. Okay, and I want to share as much as I can the serialization code and the deserialization code, right, which includes parsing, scope checking, type inference. Okay, and we've done some very initial experiment. I think we can do 2 points from this diagram at the moment, but we can do them modularly. So I'm very optimistic about this. And what you get is kind of intrinsically typed, well scoped FFI with holes, and you can kind of graph things together. You can ship them off to the SMT solver. You can read them back. You're really kind of mixing and matching various kinds of O monoids and O actions. So I'm very excited about this. And of course, you need technology to do it that lets you do kind of modular pretty printing, modular parsing. So you need a nice parser combinator library, to pull that off. But we have that technology, so it's kind of funny. Well, funny, also fun, I guess. Okay, so summarizing. Okay, we took the classical theory, secular data syntax. It was one little case we didn't deal with. Now we can deal with that. I cut a lot of corners that I didn't talk about, these kind of Kleisby by categories, and all the maths I omitted. But really, all the details are in the paper. I strongly encourage you to go and read it. Ask me questions if you have any issues. I'm on Zulek. You know where to get me. I'm only 50 minutes away. You can always come back here. And I'll stop here and take more questions. Thank you. Okay.
What would happen if you were interested in finding constructs that didn't just talk about one variable, things like patterns?
I mean, I think what's interesting about patterns is not just about one variable; it's about the substructurality of it, right? You need to get So I did mention it. I've not read that piece of work in detail yet, but there's a very recent preprint by Theo and Ranchard dealing with this theory in a substructural setting. I need to go and delve deeper, or you can ask Marcelo, or you can dig yourself as well. I think it's not quite the full story, but I don't want to say the wrong thing because I haven't read it in detail yet.
I mean, what happens is that you have a kind of more interesting relationship between what it's like to be a binding site and what it's like to be a use site than just saying there are some variables you're allowed to bind and some variables you're not allowed to bind.
I think I want to see it maybe concretely on the board, if that's okay.
Yeah.
question from online.
Yep.
Is there a reason why you would use a coproduct for sorts of like first and second equals sort versus having an embedding first into sort?
You get subset embedding. This is the
Yeah.
just because it's super cosmetic. I wanted my values to be themselves, so I wanted to choose the embedding, but computations. So sometimes it's an embedding, sometimes you retag it, and in the very first version it was just a subset embedding, and that didn't feel right because we had to do some retagging, and so I like having a coproduct diagram better because I can you know, have more control of it. I think this is the one place in the universe where I can say I want a view rather than a subset and have people kind of sympathize. Does that answer the question?
I assume so.
Okay. Any more questions? Two from the back. Bob.
So, am I right in thinking that you so prove your universal property by giving witness, which is the drawing representation?
No, actually, any initial algebra for the end of.
So it's proof you give, and then the Idris implementation, I guess, bigger implementation.
It's only the computational.
No,
Images.
no, but I have it here. You need an initial algebra for this.
Yeah.
But it doesn't need to be the Brown.
No, but
Also in Idris, you can have a view that lets me do the fold. I really just need the fold.
how do I?
Okay, but I mean, to me it's open. I don't know how to do the efficient Coder Brown if I'm doing Coder Brown at this level, right? But the inefficient one, you just plug in the fold and it all works.
Could you imagine one involving actual pointers?
Yeah, yeah. I do. I mean, this is the paella. Yeah. This is a different piece of talk I can give, but yes. I am heading that way, but it takes a while. And, yeah. Zanzi, you had a question?
Yeah. Do you know your strength, the institution, is that related to, there was a few papers called modules over modes? And
It's I think it's a different one because so they're also using modules, they're also using actions, but to me they kind of mixing together the binding structure with the substitution structure. I think, but I don't want to mistreat it. The paper actually cites a very nice recent survey by Ahrens and one of his recent collaborators, and that's really extensive and comparing a whole bunch of stuff. So I would point to them that they know much better than I could do in less than half a minute. Sorry, minus 1 minute. Any more questions? I'm happy to take them to coffee or.
From online, is there a construct which you tried to add to the call by value family of examples, but then realized it would be more difficult than you expected? I'm trying to gauge how easy it would be to use this with other constructs you haven't mentioned in the paper.
I mean, we can do all the constructs in the paper. I didn't really try to push the limits of this. It was more. I've been doing core value semantics almost all on core push value semantics all my career, and then I was trying to apply it here, and then it couldn't, right? But I mean, things like polymorphism wouldn't work here. Right? You need a different, slightly different theory, but I'm assuming it will be compatible. But it's not like I've done the work to deal with things like polymorphism. The theory is out there. I don't know if that answers the question. I'm sorry. I mean, corner pointed at substructurality. That's another aspect of syntax that I'm not dealing with it.
Thank you.
Okay. What would you need to go beyond just the computational fragment?
I would like a slightly better type theory, if that's okay. but Edwin knows this. I mean, yeah. So.
Right. So it's not just people power.
I mean, you can do. I mean, so okay. I mean, Idris is inconsistent, right? So that's something else. But assuming you think about a consistent version of Idris, I mean, Nima showed you could do it even in Martin Love, but he used function extensionality to get the uniqueness to work. So there is another theory using skew actions in the way that he's been using it that could fit here. And you could try to redo the same story that way. But I would rather just wait to get a slightly better type theory so I can quotient and have FunX. We need, so FunX to me is the biggest one, otherwise you really have to mess around with setoids. With FunX, where we have quotients, you can still do something because of the multi-categorical angle that you can impose instead. Which I can talk about later in the afternoon if someone wants to. Yeah.
Does the address implementation follow the call by push value syntax, I guess?
I mean, it implements all the definitions for end of function, pointed end of functors and so on. And once you do them, you get the substitution and the variable substitution. You get a traversal by defining an O action. And so on. You can implement call by value. I did not actually implement call by value in that library. I'm really pushing hard on the FFI because that's where you would really benefit. But yes, this could be another project for doing call by value, call by push value. And I think people do like doing call by push value in this syntax, but I've not yet done that. That will be the third example in the paper for that library. Yes, I agree. Okay, coffee time, please. See you, everyone. I can leave. Okay. I will work further for coffee if needed.